Okay, so thanks again for joining us to this third edition of AMIT. We're very happy to have Rahul Deb from Toronto, who's going to talk about multidimensional screening, buyer optimal learning, and informational robustness. Rahul, the floor is yours.
Well, thank you, Juan Carlos, for this invitation. Thanks, everyone, for showing up. For those of you who came late, I can see some faces, so just unmute yourself or turn on your camera and I'll be able to see if you want to ask a question. Quick disclaimers before I jump into the talk. This is joint work with my friend and colleague, Anne-Catherine Rossler. So she's the expert on this material. So this is my first information design paper. So you can think of me as the hype man for what's coming, and this might become clear as the talk goes on. Okay. So I'm going to start this presentation somewhat unusually by giving you a model overview, just so you guys know what I'm talking about. I'll be formal about all of these things in a second, but I feel like the introduction absent exactly what's happening is not going to make sense. So let me just quickly give you an overview of the setting. So what do we have in the setting? It's a classic multidimensional screening problem. So we have a single seller, a single buyer, and the seller has multiple goods to sell. So here there are n goods to sell with, so that's the set. The buyer has a type that's going to be theta that's drawn from some distribution on this rectangle. And the initial type distribution is common knowledge. Okay, where we're going to be different from the standard multidimensional screening problem is that the initial type of the buyer is unknown both to herself and to the seller initially. But the buyer learns about her type via a signal, and I'll be formal about all of this information. So the buyer gets some information about her type via this signal. Using this signal, she forms some posterior update about her type. And then the seller, after the buyer learns, the seller offers a mechanism, okay? And our aim is basically to study what is the seller optimal mechanism under buyer learning, okay? And I'll be precise about what form this learning takes, okay? So what we're gonna do in this paper is that we're gonna derive the seller optimal mechanism in two distinct information environments, okay? The first information environment is what we're gonna call the buyer optimal outcome. What that is that's a combination of the signal and the seller's best response to that signal that maximize consumer surplus. So if you go back to my picture over here on the previous slide, you can see that this is not scrolling well, but basically think of this as so there are different ways the buyer could learn. What is the signal? So suppose the seller knows the way the buyer is learning and decides to offer an optimal mechanism in response. What is the information that the buyer could get such that when the seller best responds to it, this leads to the highest possible consumer surplus, okay? That's one problem we're going to study. The second problem we're going to study is going to be a robust mechanism design problem. That's going to be, how does a seller screen when she does not have precise knowledge about how a buyer learns, okay? So this is going to be a mechanism that guarantees the highest profit against all possible ways in which the buyer can learn. And we're going to call this mechanism the optimal informationally robust mechanism. It's a little bit clunky, but it's descriptive. We're going to argue that these two problems have a relation, so they're not two arbitrarily distinct problems that we just crammed into the same paper. But our punchline is going to be that in both problems, the way the seller screens is by pure bundling, okay? And what that means is that the seller is only going to offer all of the goods for sale at a fixed price. Okay, so that's the punchline of the paper. All right.
Rahul, to sort of have something in mind while you present the paper. So the signals here are going to be multidimensional as well, or
they're going to be completely arbitrary. We're going to allow for completely arbitrary signals.
Okay.
Okay.
So just to fix ideas, are the outcomes going to be the same in these two environments?
Yes. But by outcomes, I mean that the seller's profit is going to be the same. The signals are not going to be the same because I'll describe this, but the seller's profit is going to be the same, and that's how these problems are related, basically. Okay, Antonio?
Yeah, I have a question. I'm not an information design guy, so my question is more on the IO side of things. I noticed in the second slides with the setup that it's a symmetric environment. So the support of all the possible thetas is on each dimension is the same. Is that right?
Yes.
And if so, is that quite important for the pure bundling result? If you had one good that was always, more valuable than another, then maybe you wouldn't get this pure bundling. I'm just positing.
So the answer is that, okay, so let me give you two answers. The answer is first, yes, the symmetry of the environment is going to be important for our result. So we're going to leverage this. But your general intuition is not exactly accurate, that if you look at multidimensional screening problems without any learning, right, pure bundling typically does not arise as the optimal mechanism. So I'm just going to give you I'm going to give you a simple multidimensional screening warm up on the next few slides, just to make precisely this point. So if you don't agree with this statement 4 slides from now, stop me again, and then I'll try to give it another shot. Okay. And so what I'm going to do is, these are basically going to be my theorems. This is effectively the end of my introduction. Once I present the statements of the theorems, I'm going to give you guys some economics and some intuition for what these theorems mean or why we should care about these results. Okay. So I'm presenting this in a somewhat non-standard way. Good. So going to Antonio's question, so when I started this project, I knew very little both about multidimensional screening and about information design. So it's been a nice voyage of discovery for me. And so again, coming from where I was, I'm going to give you just a few slides of simple warm-up going to Antonio's question, just so that we're all on the same page about the problems that are inherent in multidimensional screening. Okay, so what's the simple possible multidimensional screening setup that we can think of? Suppose we have a seller that is selling 2 goods at cost 0. So both goods have cost 0 for her. Suppose that the buyer's value for each good is theta I, that's uniformly distributed between 0 and 1. So there's going to be no buyer learning here. The buyer knows her type. Okay, and moreover, suppose that the buyer's value for the grand bundle, which is if she buys both goods, her value is just the sum of each good. Okay, so this is the simplest possible setting you can think of, for how do we think of monopoly pricing when a seller is selling more than one good? Okay, so what's a naive thing that you could do in this environment? Well, the first thing you might try to do is, well, one way in which the seller can try to maximize profits is that she can charge the monopoly price for each good. Okay, here, because each good is uniformly distributed in 0, 1, the monopoly price is going to be a half. Trade is going to happen for each good with the probability half because they're independent. And so the seller's profit is basically going to be a quarter from the sale of the first good, a quarter from the sale of the second good. That gives a total profit of a half. Okay, so this is the very basic thing, right? Now, of course, but because this is a multidimensional screening environment, the set of things that the seller can do is much more. She doesn't have to just sell each good individually. She can do much more stuff. One of the things that she can do is that she can decide that she wants to only sell the grand bundle. So what does that mean? That means that she basically decides, I'm only going to give the buyer an option that she either buys both goods or she buys none of the goods. Okay? So in this case, we can just try to calculate what is the optimal price, right, that the seller would charge for both goods. What are we going to do? Well, the first thing we need to do is we need to calculate the distribution for theta 1 plus theta 2, right? The distribution of that, if each one of them is uniform, is just going to be the triangle distribution supported on 0, 2. And so you can do, 2 minutes of algebra. If you do 2 minutes of algebra, what you'll find here is that the optimal price for selling both goods simultaneously is this number. It's square root of 2 over 3. It doesn't really matter what that number is. What's important is that it's less than 1. What is 1? 1 is the total price of selling both goods from the previous slide if you charge the monopoly price for each. Okay? So the first observation is that the seller is going to sell both goods at a lower price. The second observation is that if you basically calculate the seller's profits from doing this, her profits are going to be this number. And this number is higher than a half, which is the profits from the previous slide. All right. So the observation here is that by having access to a larger set of mechanisms, in particular pure bundling, What the seller can do is the seller can increase her profits, but this doesn't have to be at the expense of consumer surplus. So in a sense, total surplus can increase as well, right? And so in other words, basically this just summarizes the slide. So the implications is relative to the sale of a single good, you can have more profits than selling each good individually because you can screen more effectively by doing more stuff. And again, this doesn't have to be at the expense of consumer surplus. Okay, so now the natural question to ask is, okay, I give you two examples of naive things that you can do. So the natural question that the theorist would ask is like, what is the optimal thing to do? Okay. The optimal thing to do, it turns out, was solved by Greg Pavlov in a great paper as an application of a methodology. It turns out that the optimal thing you want to do is what's called mixed bundling. And so what you would do is you would basically offer the following mechanism. You would say, if you want to purchase only one good, you have to pay a price of 2/3. But I give you the option of buying both goods. If you buy both goods, you get a bundle discount. So the price, if I just add up the 2/3, I'm going to get 1/4. But now because you buy both goods, you get some bundle discount because you purchased both. Okay, so Pavlov shows that this is in fact the optimal mechanism, and it requires work to show this, right? This is in fact the optimal mechanism when you have two goods that are uniformly distributed between 0 and 1. Okay. The point I'm trying to make now is that multidimensional screening is incredibly rich. So let's now think of a simple way in which I can make this model richer. So what's one of the simplest ways in which I can do it is I can move the support. I can keep the uniformity, but I can just move the support. So instead of 0, 1, I can just translate it up or down. Okay. So now suppose I move the support instead of from 0, 1 to theta L, comma theta L plus 1. Okay, where theta L is just the lower bound of the support. It turns out that when this theta L is bigger than 0, but less than this number, the optimal mechanism turns out to actually be stochastic. So the seller actually finds it optimal to offer lotteries. Okay. When the theta L becomes large, the optimal mechanism then reverts to pure bundling. Okay. And so the point, going back to Antonio's question, is here, the fact that whether or not bundling emerges, even in a symmetric environment, doesn't really depend on the symmetry, right? Surely the symmetry plays a role, as does every other assumption, right? But you don't necessarily get pure bundling because of the symmetry, okay? And again, and so the purpose of this warm-up is to just get your head into for those of you who are not familiar with multidimensional screening, just to give you a little bit of intuition, but it's also for me to present a straw man, because it turns out that this problem is really hard. And so in particular, to the best of my knowledge, we don't know the optimal mechanism for the uniform 0, 1 case for arbitrarily many goods. So instead, if I just take from 2 goods to n goods, to the best of my knowledge, we don't know what the optimal mechanism is. Okay. And moreover, there are papers that argue that the optimal mechanism can be really weird. So for example, if instead of it being the uniform distribution, if it was the beta distribution, it turns out that the optimal mechanism can offer infinitely many menus. The menus can have infinitely many items and so on. Okay, so the bottom line basically is that standard multidimensional screening is incredibly hard and can be incredibly weird. Okay, good. So where we're going to come in is we're going to take the standard problem. We're going to seemingly complicate it by adding this learning step to it. But it turns out that this learning step is actually really going to help us, and it's going to make the problem much easier, which is stuff that Rahul can do. Okay, good. So that's my multidimensional screening warm-up. So if there are no questions about that, I'm going to jump into the formal model. Okay, very good. All right. So here's the formal model. So as I said before, the seller has n goods to sell, right? Where there are small n is the number of goods. And the set of goods, I'm going to denote by capital N, where the number of goods is at least 2 in order to make the problem interesting. Okay. I'm going to assume that the seller's cost of producing these goods is 0. Okay. This is not a normalization, right? So I'm a very candid guy. I want to put all my cards on the table. This is not a normalization. I'll be clear later on at the end of the talk about what kind of costs we can incorporate. Okay, so it matters basically that the cost is below the lower bound of the support. Okay, so in other words, that trade is efficient. All right, what is the buyer's type? The buyer's type I'm going to denote by theta. This theta is just going to be a vector from theta 1 to theta L. It's going to be distributed on this rectangle where theta H is greater than theta L and the lower bound is greater than or equal to 0. And again, this is because of the fact that the cost is not a normalization, okay? Again, going back to Antonio's question, our main assumption is going to be that these types are distributed with a joint distribution that I'm going to call F. I'm going to assume it has a positive density throughout the support, okay? And our main assumption is going to be that this F is exchangeable, right? So what does exchangeability mean? Exchangeability just means it's symmetric. So if I take the random variables corresponding to this vector of types, if I permute it across the different goods, the joint distribution stays the same, okay? I just want to point out that this does not rule out correlations between the goods. It allows for correlation. So in particular, it allows for arbitrary positive correlations, but it places a lower bound on how negatively correlated goods can be. So for 2 goods, it does not restrict the correlations in any way, but for more than 2 goods, it places a bound on how negatively correlated these types can be, okay? But again, the point is relative to the uniform distribution for which we don't know the answer or what the optimal mechanism is, we're considerably more general because we can allow for arbitrary goods and we can allow for arbitrary distributions as long as they're symmetric in the sense of exchangeability, okay? And as I flagged right at the introduction, the buyer's type theta is initially unknown to the seller as a standard in the case of screening problems, but here it's also initially unknown to the buyer and she's going to learn about it. Okay. Good. How do types map to values? So we can do a little bit better here than additive values. So let me be more specific. So given a type theta and a bundle that's a subset of the goods, so any bundle B, the buyer's utility for that bundle given her type is additive for goods that are in that bundle, but we're additionally going to allow a multiplier that depends on the bundle. Okay, so for additive values, that would correspond to the case where all of these KBs are just equal, these kappa Bs are just equal to 1. We're going to be a little bit more general than that, okay? We're going to normalize the kappa for the grand bundle. So for the entire set of goods N, we're going to normalize that to 1. And I'm going to assume that the utility when you get nothing is 0, okay? Our main assumption on this value function, sorry, Juan Carlos, you had a question.
A clarifying question, yeah. So the kappas, so do you impose any type of monotonicity on the kappas? So if I add a good to the bundle, the kappa increases or something like that, or no?
No, that's the bottom of my slide. So exactly, I'll just answer this in a second, right? The assumption that we're going to impose is this assumption here that I'm going to call weak free disposal. Essentially, what it's saying is that the buyer's utility from the grand bundle is higher than her utility from any smaller bundle. Okay, this is an important assumption that we need. And the reason we call it free disposal is precisely for the reason you would expect, is that you can throw away goods if you don't want to use them. Okay? Going back to JC's question, this is the only thing that we require. So in particular, notice that this assumption does not limit at all how the kappas for any subsets of N are compared. So for any proper subsets, B and B prime, these kappas can be related in any way, all right? And so moreover, when the lower bound of the support is bounded away from 0, we can have kappas. So this weak free disposal assumption does not rule out that the kappas for smaller bundles are greater than 1, which is the kappa for the grand bundle. And the reason simply is that if you give me one more good, if my minimum utility is higher, it's bounded away from 0, even if my marginal utility for smaller bundles is higher, I'm still okay. I'm still not violating this free disposal condition, right? So what's important in this assumption here is that the utility is linear in the type. So this is the important part of this assumption. What we like here is that we, unlike a lot of the multidimensional screening literature, we can allow some sort of complementarities and substitutability in these goods which is nice for the purpose of generality, but also turns out to have some economic content in the results that we're going to present. Okay. Excellent. So now let me go back to one of JC's earlier questions, which is how do buyers learn? So what are the signals? Okay. So as I said before, we're going to be completely unrestricted, as is the case in a bulk of this literature about the signals that the buyer could receive. So the buyer learns about his type theta by observing some signal small s, some signal realization small s, that lies in a set of signal realizations capital S. Okay. And I'm going to say that the set of the signal realizations are distributed by this object here, which is, I'm going to call it, it's a little bit clunky, but it's basically G with the set of signal realizations across the type space, such that when you're, for a given type theta, this is the conditional distribution over possible signal realizations. Okay. Because our value function is essentially linear in the type, the only thing that the buyer really cares about is her expected type, right? So when I get a signal, I'm going to have some posterior distributions over my thetas, but because my utility is linear in the type, the only thing that I really care of is what the expected value is of each one of these dimensions. Okay, so in other words, it's without loss of generality for me to consider the signal space, the set of signal realizations as just equal to the type space. And moreover, to assume that for any signal realization, the conditional expectation of my type given the signal realization is just equal to the signal realization itself. Okay, so the claim is it's without loss of generality to restrict attention to these kinds of signals, because it's just a relabeling, right? Because if I take the expected value of theta with respect to some s prime, and suppose that this was equal to some s, I can just relabel this s prime as s and change the joint distribution. Okay, so it's just we are relabeling. It's without loss of me to restrict attention to what I'm going to call unbiased signals. Okay. And so again, going back to JC's question here, notice that the set of signal realizations is just equal to the type space. The type space is a vector, right? So each type is a vector. So the set of signal realizations are also going to be vectors. Okay, very good. And so the only thing that really matters for the buyer is what is the distribution over my posterior estimate of theta. Right, so the signal, for each signal realization, my posterior estimate of theta is just equal to s. So the only thing that really matters is what is the distribution of these s's. Okay, so that's the only information of the signal that matters. And I'm going to use G without any subscripts to denote the distribution over posterior estimates of the theta vector induced by this joint distribution. Okay. Right. So in other words, the only thing that I care about is the ex post distribution over my expected type space, basically. And so what I'm going to do is I'm going to henceforth refer to distributions over posterior estimates as just signals. So when I'm talking about signals, think of this as the distribution over your ex post type after you observe the signal realization. Okay. I'm going to denote the set of signals by script G. So these are all possible distributions of posterior estimates that can arise. And again, just to reiterate, there are no restrictions here on the possible signals you can observe. So you can have signals that have atoms and so on. So it doesn't really matter. Okay. Very good. So what's a mechanism in this setting? So here, once the buyer observes her signal realization, we're in a standard multidimensional screening world, so the revelation principle applies. Okay, so it's without loss for us to restrict attention to direct mechanisms. What is a direct mechanism here going to be? A direct mechanism here is just a mapping from the buyer's private information to allocations and transfers. Okay, what is the buyer's private information? The buyer's private information is just her signal realization S. So a mechanism is going to consist of an allocation Q, a transfer rule T, which are basically the following. The allocation rule Q is just a mapping from the set of signal realizations to a distribution over the probabilities of receiving different bundles, right? So we're going to allow for stochastic allocations. That's just saying that you tell me your posterior estimate, and I will tell you what lottery you get over different bundles, okay? Because we're going to assume that utility is quasi-linear in the transfer as a standard in mechanism design, I don't need to allow for random transfers because the only thing that matters is the expected transfer. And so the transfer is just going to be a mapping from the set of signal realizations to some number. Okay. And so I just want to flag one additional thing here. I said on the previous slide that my S is basically equal to theta, but I'm going to use the S notation here anyway, just to tell you guys that these are signal realizations and not the original type. So I'm going to keep that in some sense redundant notation, even though they're the same. Okay. Very good. So the mechanism is just going to be subject to the standard IC and IR constraints. So let me just walk through the IC constraint. So if you report your type truthfully, that's the allocation you get, QS. So it's a distribution over all possible bundles. So you evaluate an expected utility of your allocation relative to the distribution over possible bundles you get. Okay, that's the transfer. If you misreport your type as S prime, you get the transfer corresponding to S prime. You evaluate your utility corresponding to your true type, but you take the expectation relative to the allocation of when you misreport. Okay, and so incentive compatibility just says that you should not misreport S as S prime, and individual rationality is going to require that the buyer gets at least 0 utility. Okay, is that clear? Right? So henceforth, whenever I talk about mechanisms, I'm going to restrict attention to the class of direct mechanisms that are IC and IR. Okay, so I'm no longer going to put IC and IR there. That's always going to be implicit whenever I refer to a mechanism. Okay, good. And so the two classes of mechanisms that are special cases that are typically studied by the literature are mechanisms called pure bundling and separate sales. And I'll just tell you what they are in words. Pure bundling, so as I already told you, our punchline, our optimal mechanisms are going to take the form of pure bundling. What is that? That's just selling the entire set of goods at a given price. So it's a take it or leave it price. You either buy all the goods or you buy none of them. Conversely, separate sales is that you charge a price for each dimension of the good. You charge different prices for different goods. The buyer is free to pick any subset of the goods that she wants, and the price that she pays for the subset is just the sum of the prices of each good in the bundle that she chose. Okay? Very good. So if everyone is happy with that, let me now describe the first of the two problems we're going to study. Okay? This is a problem that I'm going to call the buyer optimal outcome. Okay, so let me walk you through quickly what that is. So I'm going to,
sorry, did you allow just the literature on multidimensional screening? It's super complicated, but another option. So there are lotteries that you mentioned at the beginning. I guess you allow for that because you said that the mechanism can be stochastic, but there's also something called, I think it's a component price or something, where you can set prices for bundles that are not the grand bundles. Like, you have 3 goods and I post you a price for each one of them, a price for the bundle of the 3, but I also post you a price if you buy only the first 2 goods. Do you allow for that too or not?
We allow for everything. We allow for basically anything, because again, we're in Meyerson's world, so the revelation principle applies. We're allowing for direct mechanisms. You give me any mechanism that you can design or any game that you design, right? The revelation principle is going to hold, and so our direct mechanisms are going to capture them. So basically, we allow for everything. Okay. Good. But that's good to clarify, right? Okay. Okay, good. So let me start off by defining what I'm calling the buyer optimal outcome here. So I'm first going to define an outcome before I append before it proceeds preceded by the buyer optimal qualifier. So I'm going to say an outcome consists of a distribution G and a mechanism QT, okay, which has the following property. This G is a signal for the buyer. Again, remember, what is a signal? It's just a distribution over posterior estimates that could arise by Bayesian learning, okay? And QT is an optimal mechanism for the seller in response to the signal. Okay. So in other words, what is an outcome? An outcome is a way that the buyer learns. The seller knows that the buyer learns via this signal, but the seller does not know what the buyer's signal realization is. So the buyer still has private information. The seller is going to offer an optimal mechanism in response to this signal. Okay, right? And I'm going to say that a buyer optimal, okay, so maybe I should take Simon's question before I move on. Go ahead.
Either way, so the way it's presented here, it sounds like G is common knowledge at the time the mechanism is chosen. But if you just look at the at this problem here, right, and the seller anticipates that the buyer has chosen any mechanism, then this assumption wouldn't matter, right? Because then the buyer would choose G star. Or is that wrong?
Necessarily. Not necessarily.
Right? Yeah. So okay. So the right.
And so because so basically so I'm going to get a little ahead of myself, right? Essentially, here's the way you should think about this, right? If we flip the timing where the seller first chooses the mechanism and the buyer can then learn, right? In some sense, that if the buyer wanted to learn in the buyer's advantage, she's always going to learn her type perfectly. Okay, because if you learn your type perfectly, you make the best possible purchase decision. As long as there's some noise in the signal, it's possible that you may be paying for the good and buying the good when your true value for the good is actually lower than what you paid. So if the buyer was left to her own devices in response to a signal, it's always going to be optimal for her to learn her type truthfully, or like to exactly is the right
in response to a mechanism.
In response to a mechanism, yeah. Yes.
Okay, and just to get some intuition, is there some sort of what's going to come? Is this more or less elaborate form of an envelope theorem that's going to come into play here? Is that what allows you to do things?
Not exactly. So no. The answer is no. Right. Okay. So let me tell you. So let me walk you through this slide, and then at the bottom of the slide, I'll try to comment on what you just said. Okay. So I'm going to say a buyer optimal outcome is a combination of a signal and a mechanism that maximizes the buyer's consumer surplus across all possible outcomes. So formally, what is that? It's basically going to be that for a mechanism Q and T, right? What is the buyer's consumer surplus? Well, it's just her utility from consumption less the transfer that she paid, okay? Evaluated from an ex ante perspective, this is integrated with respect to all possible signal realizations, okay? So what the buyer optimal outcome is doing is it's picking a signal G from the set of all possible signals, right? Such that the seller is best responding to it. So that the mechanism that the seller is picking is the mechanism amongst all ICIR mechanisms that maximize her revenue, given that signal. Okay, right? So essentially, so Simon, if we were trying to do some envelope theorem-y type stuff, so when you say envelope theorem, from that, I understand that we actually try to compute the optimal mechanism, right? So in some sense, given the fact that it's hard to compute the optimal mechanism, even if the types are uniform, if we were to try to attack this problem in a brute force way, we would first have to solve this constraint for every possible signal. And then we would have to plug that in and try to maximize the consumer surplus across all signals, right? I don't want to speak for Anne-Catherine. She's very smart. This is certainly outside my capability. So we're going to do, so I'll give you intuition at the end of the talk. We're going to do something a little bit different that doesn't require us to compute the optimal mechanism. What we're going to do is we're going to use an improvement argument. So we're basically going to sort of conjecture what the buyer optimal outcome looks like. And we're going to show you that you give me any other outcome, I can improve on it. So that's not going to require us to calculate the optimal mechanism. Yes, JC.
So clarifying on what you mentioned before, so the fact that the buyer is always better learning his type perfectly, that's for a fixed mechanism, right? So if the seller fixes a mechanism, then the buyer is better off learning perfectly. Because otherwise, I presume some sort of argument that Catherine's previous paper would apply here too, right? So noise is good for the buyer in general once the distribution is also in play.
Exactly. So noise is good for the buyer, but what's interesting here is in the multidimensional setting, there's a different kind of noise that arises that doesn't arise in the one-dimensional setting, but that's exactly right. Okay, and I'll provide some intuition about that after I state the result. Okay, good. So is everyone happy with the statement of the problem? All right. So this is the first thing we're going to characterize. So that's my first theorem. Okay. So here's what the theorem says. There exists a buyer optimal outcome. It need not be unique. Okay, which has the following three properties. The seller's mechanism is a pure bundling mechanism. Okay, so that's the result we're going to emphasize. Going to JC's point, the signal that the buyer receives is perfectly correlated. Okay, I'll comment about this in a second, but the way to think about this is that if the buyer's original type, let's say, is independently distributed, so let's say all the dimensions are IID, the fact that the signal is introducing correlation in her ex post type, or like in the posterior estimate, this is effectively, think of this as noise. This is noise that you're introducing, but the form that this noise takes is it's introducing correlation across the values, across the different dimensions of the type vector. Sorry, okay? And similar to, for those of you who know, like JC and maybe Keiichi, similar to Anne-Catherine's job market paper, all surplus from trade is going to be realized. Okay, I'll give you some intuition about this shortly. All right. So that's the result. Let me give you a second, a corollary of this result. So this result just says that this is the outcome that maximizes the consumer surplus for the buyer. It turns out that this is also the outcome that minimizes the profits for the seller. Okay, and it's very easy to argue. Essentially, the theorem says that the seller's profit in any outcome is weakly greater than her profit in the buyer optimal outcome. So to state that mathematically, if I basically compute the seller's profit, that's the seller's profit for any given signal, right? If she so for a given signal, if she picks the mechanism that maximizes her profit, and now if we have that nature picks the worst possible signal for her, that's precisely the profit that she gets in the buyer optimal outcome. Right? So in other words, the profit that the seller receives is a solution to a min-max problem. Okay, and this is going to be going a little bit ahead. This is going to be how it's going to be related to the robust pricing problem, because the robust pricing problem is going to be the corresponding max-min problem. Okay, very good. So it's a little bit late at minute 43 in my talk. Let me give you a little bit of discussion about intuition and some economics of why we're trying to look at this, okay? So the first question is something that JC already brought up, which is, why is it not optimal? It's also related to Simon's comment. So why is it not optimal for the buyer to just always learn her value, right? So why is this not always the best? Well, the natural intuition for the buyer always learning her value is that, well, this has to help consumer surplus because she's going to make the optimal purchase decision because she has a precise estimate of what her type is. Okay, but of course the catch here is that noise in a signal will change the way that the seller screens. So the way that the seller screens when faced with the prior distribution F is different from the way the seller screens when she's faced with some distribution over posterior estimates given by G. Okay, and indeed what's happening here is that the buyer optimal signal is introducing correlation across all the dimensions of the type, right? And what that's doing is by making all the dimensions of the type perfectly correlated, it's preventing the seller from doing any kind of fancy screening. So by making these dimensions perfectly correlated, it's essentially reducing the buyer's type to a one-dimensional type. Because if they're perfectly correlated, they're all the same. And so the seller basically can't really use the difference in the type across vectors against the buyer. And it turns out that the noise you introduce in order to introduce this correlation is obviously only going to arise in the multidimensional setting. And this noise turns out to help the buyer. Okay, So what are some implications here? So essentially what this is, in a sense, one way to think about this problem is that it's a benchmark, right? Where we're thinking about what is the form of screening in the most advantageous information environment for the buyer. Okay, so in the best possible case, if the buyer could learn in the most optimal way, what form does screening take? Okay, and one thing that we show here is that basically the optimal mechanism is very simple, right? It's just pure bundling, right? If you map it back to the simple example that I gave you of the uniform 0-1, remember when I said going from separate sales to pure bundling, that could lead to a Pareto improvement, right? So because it's very hard for us in general to characterize what the optimal mechanism is for any given prior distribution, it's very hard for us to tell whether complex screening can actually benefit the buyer. So whether having the ability to offer really weird mechanisms can lead to a Pareto improvement for both the buyer and the seller. Okay, so here that we're saying that at least in the best case for the buyer, when she learns optimally, screening in very weird ways doesn't really benefit the buyer. Okay, doing something simple is actually the best possible case for the buyer.
Sorry, I know you're short on time, but I just want to make sure that I understand and also provide a reinterpretation then, which I think is pretty cool. So this perfectly correlated signal, as you said, I can think of it as basically collapsing the type vector to a one-dimensional thing. So the pure bundling, it really becomes the equivalent of a take it or leave it offer, which collapses. So there is this paper in the 80s, I think, by Riley and Zikaser that says that the best thing you can do to screen a buyer when there is a one dimension is just to make it a take it or leave it offer. You don't have to randomize, you don't have to do anything fancy. So basically what you're showing is that the optimal buyer optimal information structure reduces this freaking complicated multidimensional thing to basically a one-dimensional problem, and you can do the okay.
Right.
Cool.
And so the only thing that you have to show is that, because again, right, going back to comments by JC and Simon, in order to reduce this to the one-dimensional problem, you have to introduce noise, right? Because if the buyer knew her type vector perfectly, it's not going to be one-dimensional. And so you have to introduce this noise in order to introduce the correlation. And the only thing that you have to argue is that this noise is there's not so much noise that it hurts the buyer because she can't make optimal ex post decisions. So this noise certainly screws the seller because it doesn't allow her to screen across dimensions, but in a sense, it's also hurting the buyer because she can't make optimal ex post decisions. And what you have to show is that somehow that noise is not bad, not bad for the buyer on net, okay? But your interpretation is exactly right, okay? So let me just make one last comment about this, is that I don't want to make too big a deal about this because I genuinely view this as a theoretical benchmark, an interesting theoretical benchmark, but a theoretical benchmark nonetheless, is that this result has some antitrust implications because we typically think of, when we think of practices like tying and bundling, these are often scrutinized by regulators, especially for firms that have large market power. We're thinking of a monopolist. So by definition, we're thinking of a firm that has large market power. And in some sense, what our result is showing is that there are circumstances where bundling is not only not bad, it's actually very good for the buyer, and in the sense that it can provide the maximal consumer surplus. So if we, in a sense that, one way to think about this, if we could regulate the information that the buyer gets, we wouldn't have to regulate practices like tying and bundling by the seller, okay? Very good. So I have about 10 minutes or so, that's perfect time. Let me now tell you the second problem that we study, okay? The second problem that we study is a robust mechanism design problem. And as I told you before, this is going to be the corresponding max-min problem to the min-max problem that we studied earlier, okay? So if you give me a mechanism QT, so now again, I'm going to define a completely new problem. So just remember what a signal is, what the prior distribution is, and what a mechanism is. And I'll tell you now what the timing is going to be different. Okay, so I'm going to say that a mechanism QT is going to provide a revenue guarantee of pi if across all possible signals that the buyer gets, this mechanism gives the seller at least a profit of pi, or a revenue in this case, because the costs are zero. Okay, so that's the terminology I'm going to use. And the clunky terminology, an optimal informationally robust mechanism, I'm going to call it Q star T star. You'll notice I have different stars just so that I don't overload notation, is the mechanism that provides the highest revenue guarantee. So formally, this is going to be the mechanism that the seller picks when she knows that after she picks the mechanism, nature is going to pick the buyer signal. That's the worst possible signal for the seller. Okay, so in this sense, it's a robust mechanism design problem, because what does the seller know? The seller knows the prior distribution F. That prior distribution determines the set, these sets G, over of all possible signals that the buyer can get. So there is some structure in the problem, because those script Gs cannot be arbitrary. But over and above that, this is a robust mechanism design problem where the seller is picking a mechanism that provides the highest revenue guarantee against anything that nature does. Okay, let me make a few comments here very quick. So the first comment here is that the fact that these are maxes and mins as opposed to soups and infs, right? That's not obvious. Okay, the proof is constructive, so we show what the mechanisms are and how they're obtained. So we show that the min and the max are actually obtained. So I'm being a little bit sloppy when I write this here. Let me make one additional comment here. Something that's in the paper, but that's not on the slide, is that the fact that we allow for any arbitrary signal implies that we're technically allowing for the buyer's distribution, so these Gs, to have atoms. Okay? When there are atoms, then the way that the buyer breaks ties can matter for revenue. Okay? Typically, when we do mechanism design, we think of the buyer always breaking ties in favor of the seller, right? The seller has commitment. That's the assumption that we implicitly always make. Okay? So here you can naturally ask that when we're thinking about the robust mechanism design problem, we're taking the worst case distribution for nature, but we might also worry about the fact about how ties are broken precisely because we allow for atoms. Okay? So what we're in the paper, which is not on the slide here just because it complicates notation, in the paper, we also allow for the buyer to break ties against the seller. Okay, so in other words, over and above this min, there's another min sitting in there that says that not only are you picking the worst possible distribution, the buyer is also breaking ties against the seller. Okay, and it's for this reason that you cannot automatically invoke some sort of minimax theorem. Okay, because it's not just a min-max and a max-min problem. It's in a sense a min-max-max and a max-min-min problem. Okay? Very good. So with that said, let me give you the result. Okay? One last definition here while my slide loads. So in all of these robust mechanism design problems, as I was talking with Keiichi about his paper, is that they involve some sort of randomization. And so I'm going to say that a random pure bundling mechanism is just a mechanism in which the seller only ever sells the grand bundle, but she might randomize the price. Okay? So again, the different way to think about this is what the seller is doing is the seller is offering a menu over different probabilities of getting the grand bundle at different prices. Okay? But you're still only selling either the grand bundle, you're only selling probabilities of selling the grand bundle. You're never selling any smaller bundle. Okay, so the buyer either gets the grand bundle or she gets nothing. And the result says that there is a random pure bundling mechanism that's an optimal informationally robust mechanism. So again, the robustly optimal mechanism here takes a very simple form. It's just a pure bundling mechanism, but here we additionally need to have the price being random. Okay, and moreover, the min-max and the max-min problems for the seller have the same solution. So in other words, the mechanism provides a revenue guarantee of pi star. This pi star was the revenue that the buyer got in the buyer optimal outcome, which was the worst possible revenue the seller could get in that scenario across all outcomes. Okay, and indeed, this is the fact that these two problems give us the same revenue is how we use what we use in the proof. Okay, good. Quickly, some discussion here, some high-level intuition. So why does pure bundling arise in this setting? basically for a similar high-level reason, right? So this by offering only a one-dimensional mechanism, something that only depends on the grand bundle value, in a sense, the seller is kind of shrinking. This is very informal, hand-wavy intuition. The seller is basically shrinking the set of distributions that nature can pick against her. If she offers a more intricate mechanism, nature has more things that she can pick in order to reduce the seller's revenue. Now, because the seller is only offering a one-dimensional mechanism, the only thing that matters is what's the buyer's distribution for the grand bundle. Okay, how the other dimensions of the type vector are correlated don't matter. Okay. And so what are the implications? The implications are that, simple one-dimensional mechanisms might be useful. So let's not take the randomization too literally here, right? Because we don't really see, random mechanisms of this form. I think the economics here is just simply to say that when you have multiple dimensions, the optimal thing that you might want to do is to offer a lower dimensional mechanism, because you have to guard against less possible distributions. So that to me is the sort of high level economics insight here, right? And maybe that's one reason why we don't often think of this as a multidimensional screening problem, but basically all online streaming services that are offered with a sort of a fixed monthly fee and all you can eat sort of model are basically pure bundling mechanisms, right? Because in principle, something like Netflix or Spotify, they could sell you bundles where you buy Netflix Kids, Netflix Sci-Fi. They could offer you all kinds of different prices for various subsets of the bundle of the goods that they're offering, right? Netflix is a vendor with high market power. Marginal cost of streaming is zero. So these sorts of streaming services are good examples of things that do a decent job fitting the model. Again, I don't want to make too big a deal saying that this is the reason that Netflix does this. I just want to take the general economic idea here, that is that if there is, essentially uncertainty about what the buyer's distribution is, then it might be better to offer lower dimensional mechanisms. Okay, good. So I have, JC, should I take 3 minutes or should I take an extra 5 minutes? Perfect, great. So let me just give you intuition for the first of the two results, which goes back again to Antonio's discussion. So let me just give you some intuition about the first of the two results, and then I'll conclude, right? So again, just remember the buyer optimal outcome was basically the outcome that maximized consumer surplus. What the seller did was offer a pure bundling mechanism, and the signal introduced perfect correlation, okay? So what I want to just do in the next couple of minutes is just unpack this point a little bit, right? So it may not be obvious if the original prior distribution F is IID across type dimensions, how you would even introduce correlation of this form. Okay, it turns out it's very easy to do. So let's think about that a little bit. Okay, so here's a simple lemma, which is basically everything sort of follows from this simple lemma. Once we have this lemma, we can use arguments from the one-dimensional case. Okay, so you give me any signal G. This is a signal over the entire vector, right? So every signal gives me a distribution over the type vector. I can take that signal and I can impute what the distribution over grand bundle values are, right? So I can take the signal and impute what the distribution of S1 plus Sn is, okay? Now just observe that there are multiple signals that could potentially induce the same distribution over grand bundle values, okay? And in particular, what we're going to argue is that one of those signals is perfectly correlated. So you give me, and so in other words, what is this lemma saying? It's saying that let's start off with any signal G, okay? If you give me the signal G over the type vector, there's another signal G prime that is perfectly correlated and that induces the same distribution over grand bundle estimates. Okay, so that's this simple lemma is the main observation of the paper, right? So you give me any signal, I can take that signal, I can then compute what the grand bundle estimates are, and I can find another signal that gives me exactly those same grand bundle estimates, but this signal is in fact perfectly correlated. Go ahead, JC.
So this is where the symmetry of the distribution space matters a lot, right? Otherwise, you wouldn't be able to do this.
Exactly. Exactly. So this is where the symmetry. So now that's so as expected, JC is ahead of me. So let me just quickly explain to you how this is working. Okay.
Rahul, can I just add to that? So the additive nature also matters here, doesn't it?
The additive nature matters throughout, because what's important in all of this discussion. So by the way, hi Guillaume, I didn't realize you were at the talk, but the additive nature matters throughout, because if we didn't have these linear values, then the problem is that the buyer wouldn't just care about the posterior estimate. She would care about the entire distribution over the posterior distribution over the type theta. And that's an object that we just can't keep track of. So the linearity here matters everywhere, but in particular, it's going to matter here too. Okay, good. So let me just give you some quick intuition as to how we get this perfectly correlated signal. So here's a very simple idea. Suppose I gave you a signal of the following form. So I see for any type vector, all I tell the buyer is, here's the sum of all the dimensions of your type vector plus some noise. Okay, if the only thing that I tell the buyer is the sum of the vector of types, because the prior distribution over all these dimensions is symmetric, if the only thing that I tell you is the sum plus some potential noise, my posterior estimate over each dimension is going to be the same. So if the only information you have is the sum, so let's say, for example, just to even make this easier, let me even kill this epsilon. So the signal basically tells the buyer what is the sum of your type vector. If this is what the signal was telling the buyer, then what is the buyer's posterior estimate of each dimension going to be? It's just going to be S bar over N, because everything in the underlying world is symmetric. Okay. Now, if I add some noise, I'm still preserving the symmetry, because the only thing that I'm adding noise to is the sum of the type vector. So I'm still going to get my posterior estimates across all dimensions are going to be the same. So in other words, my posterior estimate is going to be perfectly correlated. Okay. Right. And so essentially I'm running out of time. So essentially what the argument just basically argues, like the previous lemma, it says that you give me any signal, I can find another signal that's perfectly correlated using a construction like this. And once I can find such perfectly correlated signals, now I can basically convert everything to a one-dimensional problem. Okay, so it's not enough intuition because I don't have enough time, but let me skip one slide and then let me, should I take 1 more minute, JC, 2 more minutes? Okay, fine. So let me just go straight to my conclusion slide, okay? So here's what we basically did, right? So we took a problem that's notoriously intractable, right? We added an additional ingredient to this problem. And what was surprising to us, so this was our COVID project in the sense that it has nothing to do with COVID, but we started working on this during COVID when there were lockdowns and there was nothing to do. And so we were like, this sounds like a hard problem. Let's try to play around with it. And it turns out that adding the information design component actually makes the problem really easy. So the proofs are actually relatively straightforward, okay? And what do? We basically characterize the buyer optimal outcome and the optimal informationally robust mechanism. We show one is a max-min problem, the other is a corresponding min-max problem, both of which give the seller the same value. And what's important is the qualitative result that we show, which is basically that the seller's optimal mechanism in both problems is pure quantity, okay? Now, as I said right at the outset, there are several important assumptions that go into this. The linearity of the type, that's not something that I think we can drop, because we don't want to keep track of the entire distributions over the posterior estimates. We just want to keep track of the means. So that's not something that we're going to hope to drop. But instead, things that we could potentially do is that we could try to think more seriously about the cost. So as I said before, our cost equal to 0 is not a normalization. We can allow for costs that lie below the support of the values. Basically, we need our free disposal property to work, which is that the trade of the grand bundle always leads to higher surplus than the trade of any smaller bundle. And if you have costs that lie on the inside of the support, this need not be true. So we basically need to have some sort of assumption on the costs that give us that feature of the problem, because that's a really important feature that we leverage. Okay. And the last thing that we need to do is we need to think a little bit about, whether we can incorporate asymmetry in the prior distribution. Again, I'm hoping referees are not cranky about this, given that, we allow for arbitrary goods, correlations amongst goods, we allow for non-additive values, so we can go considerably beyond what the state of the art is for multidimensional screening. But yeah, we do require a symmetry assumption. It's food for thought for future work. So let me just stop here without abusing your hospitality any further.
So before going to discussions, let me thank, please join me in thanking Rahul for a wonderful presentation.
Thank you.
I'm gonna stop the recording now, and those who would like to